And this is my video report on modeling the motion of a mass suspended from a string. Our goal was to compare the observed motion tracked from video analysis with the computational model based on the energy and momentum principles. I first analyzed the video and tracker to get the position data, and the critical step here was preparing the data. I exported only the x and y position coordinates onto a CSV file, ensuring no time data or headers were included, and then the data was fed directly into our GlowScript computational model. This was our initial setup.
Go whenever.
But I assume y is plus x.
X versus
No.
As you can see, our model simulates the motion by applying the momentum principle. And first we calculate the net force by summing up the gravitational and spring forces. And simultaneously, the model calculates the system's energies using these fundamental formulas, such as the kinetic energy, the gravitational potential energy, the spring potential energy, and the total energy. This was our observed versus predicted motion based off of tracker. Comparing the results, we see different levels of agreement. In the y direction, which is the vertical direction, we have the model in red, providing an excellent match to the experimental data, which was in blue. And we see strong alignment in both the period approximately 0.6 to 0.7 seconds, as well as the amplitude. This confirms that the spring constant and initial conditions accurately captured the physics of the dominant vertical oscillation. In the x direction, which was the horizontal, it shows us a significant phase change, and the experimental amplitude is consistently larger than the models. The prediction here is weaker, and it likely stems from neglecting minor external forces like air resistance or subtle initial velocity components that the simple model doesn't account for, as the horizontal swing is slightly sensitive. What does it mean for the energy principle? So, the question here is asking, for your model, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. So overall, yes, it is satisfied. Our defined system includes the mass, the spring, and the earth. And since all significant forces, gravity and the spring force, are internal to the system, the external work must be zero. The energy principle dictates that the total change in energy must be zero. And from the previous slide, we saw that the change in total energy is remarkably flat and centered on zero throughout the entire simulation. This flatness confirms that the model successfully conserves total energy, validating the energy principle for the closed system. For the second what does it mean question, it asks, using the data you obtained in tracker, make two separate estimates of the oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position data. Compare the two estimates and discuss. So we can estimate the periods directly from the graphs from before, and we see that the y period is significantly shorter than the x. The y period, which is approximately 0.6 to 0.7 seconds, is a faster, more dominant vertical spring oscillation. And in the x period, we have 2.0 to 2.5 seconds, which is a slower horizontal spring. Overall, the y period is significantly shorter because that motion is strongly governed by the high spring force constant. The x period is much longer because the horizontal motion is a much smaller coupled oscillation and is not dominated by the same spring force component, leading to a much lower natural frequency. The two motions are effectively decoupled oscillators with distinct periods. Therefore, in summary, the computational model was highly successful at predicting the system's energy conservation and the frequency of the vertical motion. Our analysis confirmed that the momentum and energy principles accurately describe the dynamics of the spring mass system, even when highlighting where real force motion deviates due to unaccounted for forces in the horizontal direction. And to finish off the slides, I have a snippet of my code, which includes a bunch of the constants we use in the experiment. We have gravity, which is 9.8, the spring constant, which is 9, the relaxed length of the spring, which is 0.13, and then we have the initial kinetic energy, gravitational potential energy, spring potential energy, and total energy. And then in the loop, we define these initial energies, we calculate the gravitational force and the spring force on mass by the spring, we calculate the net force, and then we apply the momentum principle. We update the spring, and we calculate the energy changes. Thank you so much.